So set theory, right? So typically one or two questions tend to turn up, right? Or rather, one question tends to turn up in the quant section. When it doesn't, we generally see an LR case as well, which turns up. Very few years where you have nothing pertaining to set theory turning up in the exams, right? So therefore, it becomes quite an important lesson, either from a quant or a DLR perspective, right? So so when it comes to sets, we need to understand that there are two basic forms of representation, right? The theory part of it. One is what is called the roster method, which is what is used pretty much, right? So wherein we say A equals 1, 2, 3, and so on till 100. So what is implied is the pattern over here we establish. There is 1, 2, 3, and so on till 100. This is the first 100 natural numbers or the positive first 100 positive integers. The same thing with the set builder notation. Again, theory aspects, not very important because typically this is not used, right? X is an element of natural numbers types, and you can say that X is going to be less than equal to 100. So all natural numbers where X is less than 100 tends to turn up. The theory part is explained in the lesson and not very important from the perspective of the exam, right? So very quickly, let me just go through the basics part of it. A null set we need to understand is represented with this. At times it might turn up, which simply means it's empty. There's nothing in it. There is a set, but it's empty. There's nothing in it. What about zero? Is that supposed to be a null set? That is not a null set because it has one element, which is zero. Zero is not nothing. Zero is something, and it's an element. If it's present, it's called a singleton set because there's only one element over here. So another singleton set is 1, 2, 3, right? These are all independent sets. Yeah. Next is an infinite set. Infinite set can also be defined as the set of all natural numbers, 1, 2, 3, dot, dot, dot. That's it. It's an infinite set, and so on and so forth, right? So let's not get too much into the theory. When we start working out the sums, we'll have a better hang of it, right? A couple of other things we need to know is A is a subset of B, right? So if A has the elements 1, 2, and 3, and B has the elements which are 1, 2, 3, 4, then A is a subset of B. B is a superset of A, right? B is a superset of A. Those are the terminologies used because A is completely contained in B and B has extra as well. B is the superset of A. And if, let's say, one element is removed, is A a subset of B? It's not. It's no longer a subset because 1 is not present over here. 2 and 3 are. 1 is missing, right? Theory part of it. Next up, when it comes to Venn diagrams, right? To typically represent unions and intersections when it comes to sets. What is union over here? So let us say we have a set over here, which is 1, 2, 3, right? I'll just close it at that. B is going to be 2, 3, and 4. I think all of us know at the stage, A union B is simply everything comes up once, right? You should either be in A or in B. 1, 2, 3, and 4 also is included. A intersection B simply means it's present in A and B. What is present in A and B, both of them? Only the elements 2 and 3, right? Only the elements 2 and 3, that's common for both of them, and that's it, right? So these are union and intersection. Complement, right? So let's say we define a universe right now and say that comprises of 1, 2, 3, 4, and 5. And then a complement, or we could use A and C over here, right? It simply means whatever is not in A, but present in the universe. Complement, whatever is outside of A, but present in the universe. And that's the elements 4 and 5, right? So that's the complement of a set. We could also have something like A minus B, which means whatever is present in B, if you remove from A, what is left over is just going to be 1. Now, this is hardly asked, right? So we don't need to get into it in too much detail, right? Whatever is present in B, if I remove 2 and 3, then I'm left with just 1. It's not often asked, but it can be looked at from a Venn diagram perspective, right? So A and B, you have 1 here, you have 4 here, you have 2 and 3, and in the universe, you're also going to have a 5, right? Which is outside. Now, A minus B, remove the B, you're left with just 1 over there in that set, right? So 2, 3, these are not number of terms, it's just the set elements which are there in these regions, right? So Venn diagram is what is used to represent the different figures. Now, if you look at A union B, it's the entire thing, right? So it's 1, 2, 3, 4, all of them. If you're looking at A intersection B, only the common region, it's going to be this. So 2, 3 over here. And if you're looking at A complement, other than A, what is outside? 4 and 5, right? So 4 and 5, only B and outside of it. A minus B. From A, remove B, you're left with just 1, right? That's it. With a Venn diagram, it becomes easy for us to figure these out, right? So this is a two-set Venn diagram, right? So this is a two-set Venn diagram. I think at this stage, almost all of us would be knowing this from school, right? Don't need to be going into it in too much detail. But from a formula perspective, they would have taught us something, which is N of A union B, right? What is that? N of A plus N of B minus N of A intersection B, right? If we want to apply this, N of A union B is nothing but 1, 2, 3, 4, right? All of them. So if you want to put the number of elements over here, A union B, all four, I mean, all of them put together is going to be 1, 2, 3, 4 elements equals number of elements in A, it's 1, 2, 3, 3 elements there. Number of elements in B, that's 2, 3, and 4, 3 again. Minus what was common between them, subtract once, because it got double counted, right? With both 2 elements, 2 and 3 have to be subtracted once. 6 minus 2 works out to be 4, right? So this is a formula. I think all of us should be knowing it at this stage. Please, we need to note these down, right? Okay. So very quickly, let's move to a 3-set Venn diagram, understand the different regions over here before we take up some. In fact, we'll finish up the concepts and then take up about 6 to 7 examples over here in set theory, right? Past CAT questions. Now, a 3-set Venn diagram, how is that going to look? All right, so let me just draw something clearly. So we have, yeah, so we have a set here. Next up, I would want to move this, right? Let me just move that, yeah, to the right a bit. And I get the third one, move it to the bottom, okay? Now, so we have a 3-set Venn diagram. Typically, we also use a rectangle over here to just close it up. And let's make the observations over here. So A, B, and C, right? We know that the middle region over here is belonging to all 3 sets. So let's call them A, B, C, D, E, F, G, and H. H is outside, right? And this is the universe. Now, how many distinct regions are there in this Venn diagram? There are a total of 8. The reason is, if it's a 3-set Venn diagram, there are 2 cube 8 regions. If it's a 4-set Venn diagram, it's 2 to the power of 4 because there are 4 sets, 16 distinct regions. We'll see next, right, when it comes to that. Now, the 8 distinct regions, I have labeled them as A, B, C. They denote the number of elements in each of these regions over here, right? So first up, the formula which we need to know is N of A union B union C, right? It's hardly used, but we can remember it. It's not too difficult. N of A plus N of B plus N of C minus N of A intersection B minus N of A in B intersection C minus N of C intersection A plus N of A intersection B intersection C, right? How do we do this? We've seen this in the lesson. You can write these down if you want: A, D, F, G, B plus D plus G plus E, and so on for all of them. And when they all get cancelled, you will be left with just A, B, C, D, E, F, G once, right? All appearing once. Or another way to look at it, when I'm adding N of A, N of B, N of C, the regions which are going to come twice are going to get double counted. It's a part of N of A and N of B. So I have to remove them once. But what happened as a result? The region which comes thrice, right? 3 times for a part of all 3 sets. It got added 3 times, it got subtracted 3 times. So I have to finally add it back once. If you want to logically look at it that way. If it's clear, it's great. If not, it's still fine. Just understand the formula over here and proceed, right? Proceed. Now, more important is not the application of this. It's the application of P being the set. I mean, P being the number of elements. Okay, let's put it this way: number of elements belonging to exactly one set. One set over here in exactly one set, right? And what is that going to be? Exactly one set in this particular case is A plus B plus C. A plus B plus C. Q over here are those which are going to be belonging to exactly two sets. Exactly two sets is D plus E plus F. And R over here is all three sets. And that's going to be yeah, G, only G over here. X can be none of the sets. Now, this is the part what I'm going to come up over here. That's going to turn up a lot in the exam, right? The application of it. The first step, the universe equals P plus Q plus R plus X, right? Sum of all of these. None of the sets, only one set, only two, and all three. N of A union B union C, right? That simply means each of these are going to come once. Outside is not going to be included, right? Which was H. So it's simply P plus Q plus R. N of A union B union C is all those appearing in exactly, occurring in exactly one set, those in exactly two sets, and those in all three sets. The third one over here is N of A plus N of B plus N of C, which is going to be P plus 2Q plus 3R, and we will be using this a lot. N of A plus N of B plus N of C. When I know the totals over here given to me, the totals given over here, it's P plus 2Q plus 3R, because ADGF, BDGE, CFEG, A, B, and C got added once. So P is once. Now D over here got added for N of A and N of B. E got added for N of B and N of C. F was for N of A and N of C. So twice. Those occurring in exactly two sets got added twice. So plus 2Q. And G over here was a part of all three of them. So plus 3R. Right. So these three are really important and more important than way more important than what you see above over here with this particular formula. This is what is going to be used extensively while solving these questions. Okay, so next up, we're going to be looking at a four-set Venn diagram. All right. When it comes to a four-set Venn diagram, we know how to form it. It's going to be, again, there are two ways of doing it. I'm more comfortable with what I've been teaching, which is going to be four rectangles. All right, so two vertical rectangles, right? Second one starting from the midpoint, a little shorter, and then two horizontal ones, and again, something starting over here from the midpoint of it, right, of the breadth, and you get something like this. So once you're done with this, you need to understand those belonging to four sets, right? Now, again, we'll have P, Q, R, and X, R, S, and then X. X is whatever's outside, right? Now, those belonging to all four sets, right? All four sets. Let me just label it over here. That's going to be S. Exactly three sets. Remember this, right? How do I write this S over here? We have a 3x3 grid over here. And in that 3x3 grid, the middle one is going to be a part of all four rectangles, and that is S. The R's belonging to exactly three sets are going to be up, down, left, and right of this S. These are my R's belonging to exactly three sets. The Q's over here, we're going to have six of them because we have a total of four sets. And for four sets, we need to find the different combinations of belonging to exactly two sets. It's going to be 4C2, which is six regions. So that's going to be in this matrix, the remaining parts, Q, 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 done. Two more, which are going to be over here, belonging to these two rectangles and belonging to these two over here. Those are my six, right? Six. Then the P's are those belonging to exactly one set and exactly one set. And we have got them over here, right? X over here is none of the sets, yeah, none of the sets, and that's outside. Those belonging to none of the sets is going to be outside. Total of how many regions? We had 1x and 1s, 2. So we had one of this, and then R's there were 4, P's there were 4, and we had 6 of Q. You add this up and you're going to get 16 because 2 power 4, 4 sets over here, 2 to the power 4, total of 16 different regions over here, right? 16 different regions. So what are the formulae pertaining to P, Q, R, S, X? We need to remember the universe over here is going to be the sum of P, Q, R, S, and X, all of them appearing once. Now, N of A, union B, union C, union D. If this is going to be my set A, set B, set C, and set D, then N of all the unions is going to be everything, P plus Q plus R plus S, but for X. X is not going to come. X is not inside, it's outside. Now on to the last one, N of A plus N of B plus N of C plus N of D is going to be what? There I had P plus 2Q plus 3R. That continues, but I have one more letter right now. That's on 4 sets, so I add a 4s. If it were 5 sets, it will be P plus 2Q plus 3R plus 4s plus 5T, right? When I'm going to be adding all the number of elements in each of these sets. Now, this is pretty much it, right? What you're going to be using when it comes to this. You don't need to have one unified formula in terms of N of A plus N of B plus N of C plus N of D minus N of A intersection. You don't need to get into all of that over here. This is it, right? So you get this and you should be able to solve any of the LR cases or like quant questions pertaining to 3 or 4 set Venn diagrams. So now let's look at a concept of maximum minimum when middle region is not known, right? We can just create a very quick case as well over here pertaining to this. So let us say we have A, B, C over here, and we can define N of A, N of, okay, let's say we define N of A intersection B over here, belonging to both of them, right? N of B intersection C, this could be given in the question. C intersection A can be given in the question. Let's take them to be 20, 35, 40, right? So if that is the case, the middle region is not known, which is belonging to all 3 sets. Take that to be X, right? Take that to be X. Then A intersection B, this region over here. Entire region was 20. So this region alone is going to be 20 minus X, right? Only in A and B, but not C. That's going to be 20 minus X because A intersection B is going to be the entire bit. And if entire thing is 20, remove X and you get this as 20 minus X. Likewise, for B intersection C, we're going to get a 35 minus X, and here we're going to get a 40 minus X. Next up, we could be given a few other figures like N of A, N of B, and N of C. What do I have as the total so far? I have a 60 minus X. And then I can be given a total over here, which would then tell me that what this number is going to be. Let's say A is 100, right? As this is 60 minus X, from 100, if I have to remove 60 minus X, right? Sum total of this is 60 minus X because 60 minus X plus X is cancelled, negative 60 minus X. If I remove from 100, 60 minus X, I'm going to get X plus 40, right? X plus 40 over here. And here I have a total of 55 minus X. And what if this total is going to be a 50? If I'm going to remove a 55 minus X from this, I'm going to get a value of X minus 5, right? If P over here is just going to be 50, and only if I get an X minus 5, or all the X's are cancelled, and the minus 5 with the 55 adds up to 50. And C over here can be, let's say a 90, right? Now, how do I do this, right? Another way of doing this, if I'm told that N of C is 90 over here, to find this missing one, I need the variables to be removed because I have a constant here. A minus X, X, and a minus X. I need to have a plus X. 40 plus 35 over here is 75. I need 15 more to bring it to 90. This is a way to find this as well, right? So we could be given a question this way with these figures in a group of people. 100 like tea, 50 like coffee, 90 like milk, 20 people like both tea and coffee, 35 like milk, coffee and milk, and so on and so forth. What is the minimum number of people? and you can have questions around that. So let's create two, right? So what is the minimum number of people who are a part of B, but not so a part of B, but they are not a part of but not all three sets. Minimum number of people in B, but not in all three, right? But not in all three sets, right? That could be a question. Or you could have something like minimum number of people in B, and exactly minimum number in B and exactly one other set, right? What is that going to be? In B and exactly one other set, it's either this or this, right? Both of these. 20 minus x is in B and A only. 35 minus x is in B and C only. Exactly one other set. So you add this up and you're going to get a 55 minus 2x. Let's create another question. What is the max number of people in let's say in C, or I can create a min again. Sorry about that. Minimum number of people in only C. Let's keep it simple, and that's going to be x plus 15. Now this is the catch over here. Now what are the values x can take for minimum and maximum and all of that, or minimum and minimum? It looks like I have to take the same values, but it's going to be slightly different. Now first up, I need to look at this particular Venn diagram over here and find out the minimum or the maximum values x can take. Yeah, minimum or maximum values which x can take. And how do I get to know those? And that's going to be from all those regions where there is a minus symbol involved. Right? When I have a 20 minus x, 35 minus x, and 40 minus x, they cannot become negative over here. So the max value, it tells me, the max value of x equals, it tells me I have to take the smallest coefficient, smallest constant, and that's 20. Max value of x is 20, right? Why is that so? If x becomes 21, then 20 minus 21 makes it minus 1 over here. That's a problem. So where I have a minus x, it defines the upper limit for me for x. Where there's a minus x, it defines the upper limit. The max it can take is 20. I have to look at the lowest constant. That has to be satisfied. So therefore, it has to be 20, right? Remember that way. Where there's a negative coefficient for x, that defines the max value. And take that smallest constant 20. Now with 20 over here, this becomes 0, but the rest are going to be positive and everything is satisfied. Next, if you're going to be looking at the min value over here, min value of x, or minimum, what is the value? So I have to look for a minus constant. The minus constant is there only at one place, and that's x minus 5. X has to be a minimum of 5. If it is less than that, if it is 4, then it becomes negative over here. So therefore, the minimum possible value of x is going to be 5. Now, which value should I substitute? Given that I've asked for minimum in both places, does it mean that I take the minimum value of 5 and substitute in both places? No. Why? Because now in 55 minus 2x, if the entire 55 minus 2x should be minimized, then whatever is being subtracted should be maximized. Right? Only if I put the largest possible value of x over here, does 55 minus 2x will get minimized. So I have to put 20 over here. 20 into 2 is 40. Subtract from 55 and you get a 15. Now the minimum value of x over here, it's a plus x plus 15. Here I'll put to lower this, the smallest value x can take is going to be 5 plus 15, right? 5 over here. So 5 plus 15 is going to be the value for only C. 20 becomes the answer over here. So the last concept over here before take the examples, min and max number of elements in all sets, right? Minimum number in all sets, there's a specific formula for that, right? So if the universe is defined as 100%, let's say, if the number of people in A is given as 90%, for instance, number of people in B is given as 80%, number of people in C is 75%. There are only 3 sets. What is the minimum number of people n of A intersection B intersection C, right? Belonging to all three sets. And what is the max over here? Belonging to all three sets over here, right? So what is the maximum I can have under all three sets? So I can have a 75% over here belonging to all three sets, but the minimum under all three sets, this is the way we do it. It's the universe minus of n of A dash plus n of B, not in B, n of not in C. So the universe of 100% minus how many are not in A? 10% are not in A, right? And how many are not in B? 20% not in B and 25% not in C. And we're going to get 100 minus the sum of these, which comes to 55%. And that gives me 45%. 45% is the minimum number of people in all three sets. 75% over here, the smallest of the lot, is the maximum number of people in all three sets, right? I can't have anything more than 75 because if I say 76% in all three sets, but set C has only 75% of the people, where is the extra 1% coming from? So therefore, for this, I have to take, for the maximum, I have to take the smallest of the numbers, right? For the minimum, we work it out this way. All of you clear with this? You could get a direct question around this here. The universe minus not in A plus not in B plus not in C. This, if you want, you write it down, memorize it. At this moment, I don't care, but it has to be done. Now, this is a good question, right? Again, from one of the tough years, but yeah, so if you're just gonna make the Venn diagram, it's gonna be quite easy, right? What we have, each of 74 students in a class studies at least one of three subjects, H, E, and P. So which means each of these students are going to be falling under one of these. Nothing is outside, nobody is outside. The universe is 74. 10 students study all three subjects, done. While 20 study H and E, but not P. Not in P, only H and E. That's 20 of them, fine. Every student who studies P also studies H, E, or both. So that means there is nobody over here. Only P is nobody, because anybody who's studying P is also doing at least one of them. Outside, I mean, just P is 0. If the number of students studying H equals that studying E, so this H and E, H circle is equal to E circle. Common is this. That means uncommon part should be equal. So this uncommon part should be equal. So let's call this entire uncommon part X, right? Entire thing is X. Then X plus 30 plus X. X plus 30 plus X equals 74. So therefore 2x equals 44, x equals 22. So x is 22. What is asked is number of students studying in H. H over here is 30 plus x. And that x we found to be 22. So you substitute 22 here and you get 52. And that becomes the answer for this question. So if among 200 students, 105 like pizza and 134 like burger, right? N of P is given, N of B is given. Then the number of students who like only burger can possibly be. There's a possibility for that. There are a total of 200 students over here. Those who like only burger, right? What can that be? So total of 200 students. How do we split it up, right? How do we split it up? What approach do we possibly take over here, right? Several ways of doing this, right? Several ways of doing this. One is to, go in for a Venn diagram and just quickly try to understand, right? And see as to what we get. Observe a little, right? So we're going to have 105 and B over here. That's given as 134. If we have an X over here, this is going to be 105 minus X. And this is going to be a 134 minus X over here. The number of students who like only burger can possibly be. Sorry, with that, we could have gone for X over here, right? The possible number of this is what we're looking at. Go the other way around then. Sorry. Yeah. So if this is X, then what is this going to be? This is going to be 134 minus X. What is this going to be? 105 minus of this. which is x plus 29, and we have 105 plus x here. Grand total is 200. Grand total is 200. If this is 105 plus x, grand total is 200, and you subtract this, we're going to get 95 minus x over here outside, right? Outside this. Once you've found the values of these regions, then I can say the minimum and maximum values x can take, right? X has to be a minimum of 95, x has to have a minimum value over here, or rather a max over here, right? A max of 95. It can't go past it, right? So what is the minimum value it has to take, right? So is that clearly emerging over here? Actually, there is a slight mistake, right? This should have been a minus 29, right? Only then it's going to add up. 105 minus of this would have been a minus 29, right? Which is what I was looking for. So the max value over here is 95, right? The upper cap we had seen over there, and that concept pertaining to the middle region being not known. But here, it was in the middle exactly, but yeah, let's start over here. And x min value over here is 29. So between 29 and 95, there's only one value over here, which is option 3, which is 93. Okay, so let's look at question 3 over here, right? So question 3, a couple of ways of doing this, right? So if a equals 6 power 2n minus 35 to the power f, 35n minus 1, where n is 1, 2, 3, and so on, and b is 35 into n minus 1, and so on, which of the following is true? Neither every member of A is in B, nor every member of B is in A. Okay. At least one member of A is not in B. Every member of B is in A. So all of that. All right. So fine. If you want a couple of values for n, you can substitute. If you substitute n is 1, we're going to get 6 square. 36 minus 35 is 1. 1 minus 1 is 0. B, when you're substituting 1, what's happening here? 1 minus 1 is 0. 0 is also there. Okay, fine. 0, comma. Next, if you is going to be 35 over here, 70 over here, and so on. And what about this? If you're going to substitute a value of 2, that I know, which is 6 power 4, which is 1296. 12696 minus 1 is 1296 minus 70 minus 1. So 1296 minus 71 becomes 1225 and so on. Then it becomes very big, right? Clearly, every member of B is in A is definitely wrong. At least one member of A is not in B. Can I say 1225 is definitely not in B? I don't know. At least one member of B is not in A. This part is correct. The first part I have to check. First part is the same over here. No, at least one member of A is not in B. The other way around. Fine. Neither every member of A is in B, nor every member of B is in A. Neither of it is true. Every member of B is in A. Not the case. This is correct. What about the first one? So now the question is every member of A there in B or not? Now, if you're just going to compare the options and only that, at least one member of A is not in B. Neither every member of A is in B. Both of them are supposed to be true. If one is true, the other is also true. Both options are correct, right? And this is wrong, right? Can two options be correct at the same time? No. We could just rule it out that way and say this should be correct, making both of these wrong, and that is the only way possible, right? Both of these are going to have the same thing. Either both are correct or both are wrong. And there's only one way you can close it out. That's one way to do it, by just looking at the options. The other is to see if, 1225 is going to turn up over here. Here I have a list of 35 multiples. Am I going to get 35 multiples over here? Let me rewrite this. I have a 35n, which is very good. And here I have a 6 square whole power n minus a 1. Now 6 square whole power n minus, I can make it 1 power n. What can I say about a power n minus b power n? It's always divisible by a minus b. And what is a minus b over here? It is always divisible by 6 square minus 1 for sure. And 6 square minus 1 is nothing but 35. So a power n minus b power n, number theory, we've seen this. A power n minus b power n is a minus b into a power n minus 1 plus a power n minus 2 into b plus a power n minus 3 into b square and goes on to b power n minus 1. So it's definitely divisible by A minus B always, and A minus B over here, 6 square minus 1 is coming to 35. As this is a 35 multiple, this is also a 35 multiple. It is going to be in the list of 35 multiples always. Every term over here is going to be there. So every member of A is going to be in B, and at least one member of B, 35 or 70 and all of that is not going to be in A. Option 4 becomes the answer. These will have to be wrong. No, these are wrong. So question 4, all right, let's just do this question. For two sets A and B, a triangle B, right? So A delta, we'll call it A delta B, denote the set of elements which belong to A or B, but not both, right? I want it in A or in B, but not both. The common I don't want. So if P is 1, 2, 3, 4, and Q is 2, 3, 5, and R is something else, S is something else, number of elements in P delta Q. Let's start with that. P delta Q is going to be what? P and Q, the common is 2, 3. I don't want that. I have 1, 4, 5, and 6. Right? I'll just put, yeah, because my curly brackets are bad. I'll just use this. And next is going to be R and S. I have to do the same. R delta S. R delta S, the common over here are, so 2, 4, 9, 10, I have a 9. I don't have a 2, 4, or 10. So I'm going to have a 1, 3, 7, 8, 2, 4, 10. Now, between these two, I need to put another delta. What's common between them? What's common I'm going to remove. I don't want them. 1 is off, 4 is off, and the rest of it, 5, 6, that's it. So 2 elements over here, 1, 2, 3, 4, and 5. 2 plus a 5 elements, that's a total of 7 elements. Number of elements over here is going to be 7. They're going to be 5, 6, 2, 3, 7, 8, and 10. Right. So let's look at question 5. So a club has 256 members, of whom 144 can play football, 123 tennis, 132 cricket, and all of that. Moreover, 58 can play both football and tennis. That is N of F intersection T. Then cricket intersection T is tennis is going to be 25. Football intersection cricket is given. So this is N of A union B union C is 256, right? Every member can play at least one game. So therefore, N of A union B union C is 256. N of A, right? We'll just call it A, or it's going to be confusing. So let's just call it F. And this is going to be F, T, and C, right? F union T union C. And then you have N of T over here, N of C over here, and you have the intersections. So 256 equals N of A union B union C, right? Or F union T union C equals N of F 144 plus 123 plus 132 minus N of F intersection T 58 minus 25 minus 63, and then a plus N of A intersection B intersection C, common to all of them, right? So here, this is one of one of the very few questions where you can apply the formula directly and you get the value and you can just close it out, right? 144 plus, this is 255 plus 144, which is 399, minus 58 and 25 is going to be 70, 83, 83 plus 63 is 146. 399 minus 146 is 253. 253 you bring here and you get 3 equals N of A intersection B intersection C. So quickly draw 3 circles. You have 3 in the middle and F, T, and C. And what do I need to find? I need to find the number of members who can play only tennis. Only tennis is what I have to find. Okay, so tennis I know is 123. Okay, what about F and T? F and T together, that's going to be 58. 58 minus 3 is 55. And tennis and cricket, I want to know. Tennis and cricket is going to be 25. So 25 is the total region. 25 minus 3 is 22 over here. So what is the sum of all of this? Sum of all of this is going to be 55 plus 25, and that's coming to 80. That 80, if I subtract from 123, I'm going to get 43, so that the entire circle is 123. So 43 is what is asked, and that's the answer here. So this one over here is a seemingly difficult question, right? So what do we have here? Students in a college have to choose at least 2 subjects from chemistry, maths, and physics. I've known it as MPC. Let me just write it that way. Yeah, just a freehand, M, P, and C. they have to choose at least two. Exactly one is not possible. So 0, 0, and 0. The number of students choosing all three subjects is 18. All three is going to be 18. Fine. Choosing mathematics as one of the subjects is going to be 23. And physics as one of them is going to be 25. The smallest possible value for those who would choose chemistry. Chemistry, I have to minimize smallest. Okay. So what do we do over here? We need to work with a variable, right? One of the missing reasons you can take a variable a over here. Of this 23, 18 is done. The remaining two should add up to 5. If one of them is a, the other is 5 minus a. Now these two reasons add up to 23 minus a. And if I add something, I should get 25.
2
23,
plus A.
yeah. So 23 plus 2 is what is coming to 25. The minus a should be cancelled. So I put a plus a over here. Now, what is going to be the total for chemistry? It's 18 plus 2, 20, and 20 plus 2a over here, right? 20 plus 2a is what we get over here. Now, what is the smallest possible number of students who could choose chemistry? A can take a value of 0. It's perfectly fine. No region is getting negative. Smallest possible value for A over here is 0. So 20 plus 0, 20 it is. Option 2 is the answer here. Let's look at question 7. In a class of 100 students, 100 is defined, n is 100, universe is 100, 73 like coffee, 80 like tea, 52 like lemonade. It may be possible that some of the students do not like any of these drinks. X outside also is possible. Then the difference between the maximum and minimum possible number of students who like all the three drinks. So we've just seen this, right? So the maximum possible is going to be the smallest set. So the max for all three, max of all three is going to be 52. Okay. The min over here of all three, those belonging to all three sets, is going to be the universe, which is 100 minus of n of a bar, right? The first one, those not, I mean, coffee. So let's call it C bar, right? Those not liking coffee is going to be 27 plus those not liking tea is going to be 20. Then those not liking lemonade over here is going to be 100 minus 52, which is 48. If you add this up, 47 plus 48 is 95. 100 minus 95 comes to 5. What they're asking is the difference between the max and the minimum. 52 minus 5, 47, right? That becomes the answer here.